In 1900, a group of sponge divers, sheltering from a storm near the small Greek island of Antikythera, pulled something from the seabed that took the next 100 years to begin to understand. It looked, at first, like a corroded lump of bronze, one artifact among many recovered from an ancient Roman shipwreck dated to approximately 60 BC. It was catalogued, set aside, and largely ignored for decades, while the more visually striking pieces from the wreck, marble sculptures, glassware, jewelry received the attention of scholars and museums. It was not until 1902 that an archaeologist named Valerios Stais noticed something in the corroded mass that should not have been there. Gears. Small, precise, interlocking gears of a complexity that the ancient world was not, by any existing model of technological development, supposed to possess. The object is now known as the Antikythera Mechanism. It is the most studied single artifact in the history of archaeology, and after more than a century of analysis, X-ray imaging, CT scanning, polynomial texture mapping, the combined effort of engineers and classicists and astronomers and mathematicians from institutions across the world, what has been established about it is extraordinary. It is a mechanical computer. It calculated the positions of the sun and moon, predicted lunar and solar eclipses on an 18-year cycle, tracked the timing of the Olympic and other Panhellenic Games, and modeled the irregular motion of the planets across the sky. It did all of this with a system of at least 37 interlocking bronze gears, housed in a wooden case roughly the size of a shoebox, operated by a hand crank, with front and back dials whose inscriptions are still being decoded. The next mechanism of comparable complexity that appears in the historical record is the mechanical clock of medieval Europe more than 1,000 years later. What happened in the intervening millennium to the knowledge that produced the Antikythera mechanism is a question that no scholar has yet been able to answer with anything approaching completeness. And the Antikythera mechanism is only the beginning. The standard account of the mechanism situates it within the tradition of Greek astronomical and mechanical philosophy, a tradition that includes figures like Archimedes, who is known to have built mechanical celestial models, and the school of thought centered on the island of Rhodes, where the mechanism's dialect inscriptions suggest it may have been made. The ancient Greeks were sophisticated astronomers and capable engineers, and the mechanism, in this reading, is a remarkable but not categorically impossible achievement of that tradition. This account is not unreasonable. It is supported by textual references to ancient mechanical devices that, while no examples survived, are described with enough specificity to confirm that such things were attempted. What the account does not fully address is the depth of precision the mechanism required. The gear ratios encoded within it, when analyzed by modern engineers, reflect an understanding of astronomical cycles, particularly the Metonic cycle of 235 lunar months and the Saros eclipse cycle of 223 months, that required not only sophisticated mathematical knowledge, but the sustained, multi-generational observational record from which that knowledge could be derived. Somebody, over a very long time, watched the sky with extraordinary care and encoded what they learned in a device so exact that modern replicas, built with the full benefit of contemporary precision manufacturing, are still struggling to match every aspect of the original's function. The knowledge that produced the Antikythera mechanism did not appear from nowhere. It had a history. And the full extent of that history, what else it produced, what other devices and systems and understandings it encompassed, is almost entirely lost. In 1938, a German archaeologist named Wilhelm Koenig was cataloguing objects in the Iraq Museum in Baghdad when he came across a ceramic jar, about 14 centimeters tall, containing a copper cylinder and an iron rod, all sealed with asphalt. It had been excavated from a site near the village of Kujut Rabu, southeast of Baghdad, and dated to the Parthian period somewhere between 250 BC and 224 AD. Koenig examined the object and arrived at a hypothesis that the broader archaeological community received with varying degrees of skepticism, that the jar was a galvanic cell, a battery, that when filled with an acidic liquid vinegar, lemon juice, grape juice, the copper and iron components would produce a small but measurable electrical current. Subsequent reconstructions, conducted by multiple independent researchers, confirmed that the device does, in fact, generate electricity when filled with an acidic electrolyte. The voltage is modest, somewhere between 0.8 and 2 volts, depending on the electrolyte used, but it is real. The chemistry works. What the archaeological community has never agreed upon is what the electricity was for. Electroplating has been suggested. Some objects from the same period and region do appear to have very thin metallic coatings that could theoretically be electrolytic deposits. Pain relief has been proposed, based on ancient textual references to fish that produce electrical fields being used therapeutically. Religious ritual is another possibility, in which an imperceptible electrical charge from a sacred object might have been interpreted as divine presence. The conventional position is that the object was probably a container for storing sacred scrolls, and that its resemblance to a galvanic cell is coincidental or, at most, an accidental discovery of electrical effects that were not understood as such and were never systematically developed. What this position cannot fully account for is the specificity of the design. The selection of copper and iron as the two metals, the use of asphalt as a sealant, the particular proportions of the components, these choices are not arbitrary. They are precisely the choices you would make if you intended to create a galvanic cell. Whether that intention existed, and what knowledge it rested upon, is a question that the object itself cannot answer. In 1898, a wooden object was excavated from a tomb at Saqqara, in Egypt, dating to approximately 200 BC. It was catalogued as a bird, a stylized wooden bird carved with evident skill, its wings outstretched, its body tapered to a point at the tail. It was filed away in the Cairo Museum and forgotten for the better part of a century. In 1969, an Egyptologist named Khalil Messiha was examining the museum's collection of wooden bird artifacts when he noticed that this particular one did not quite look like a bird. The wings were set at a dihedral angle, angled slightly upward from the body rather than flat or drooping. The tail was vertical rather than horizontal. The body was teardrop-shaped in cross-section. These are not the features of a decorative bird effigy. They are the aerodynamic features of a fixed-wing aircraft. Messiah's claim that the Saqqara bird might represent evidence of ancient Egyptian knowledge of aerodynamic principles, possibly even of functional gliding flight, was received skeptically. And that skepticism is warranted. There is no textual evidence in the Egyptian record of flight. There is no supporting archaeological context that would suggest the Saqqara bird is part of a broader aeronautical tradition. The conventional interpretation that it is a stylized votive offering, a bird of symbolic or religious significance made by a skilled craftsman who happened to produce a shape that also has aerodynamic properties, is entirely defensible. What keeps the object from settling comfortably into that interpretation is a detail that the conventional account tends not to linger on. A model built to the Saqqara bird's exact proportions, when placed in a wind tunnel with a small rudder added to the vertical tail, generates lift. It glides. Not efficiently, not in any way that approaches the performance of a functional aircraft, but measurably, in a way that a purely decorative bird shape would not be expected to. Whether the craftsman who made it knew this is unknowable. Whether it matters is a question worth sitting with. In the courtyard of the Quwwat-ul-Islam Mosque in Delhi, there stands a column of iron that is approximately 7 meters tall and weighs more than 6 tons. It was erected, according to its Sanskrit inscription, in the 4th or 5th century AD, approximately 1600 years ago, as a flagstaff in honor of the Hindu god Vishnu. What is extraordinary about the Delhi iron pillar is not its age, nor its size, nor even the engineering required to cast and transport a single shaft of wrought iron weighing 6 tons in the 4th century. What is extraordinary is its condition. The pillar has not rusted. After 16 centuries of exposure to the weather of the Delhi plain, including the monsoon rains that produce some of the most aggressively corrosive atmospheric conditions in the world, the pillar's surface displays a level of oxidation that modern metallurgists, when they first examined it systematically in the early 20th century, simply could not reconcile with their understanding of iron's properties. Analysis conducted in the late 20th and early 21st centuries found that the pillar is composed of unusually pure wrought iron purer than anything that could be produced by the conventional metallurgical techniques of the 4th century AD as they are understood today. Its surface has developed an extremely thin layer of a compound called misoite, a crystalline iron-hydrogen phosphate that forms a passive barrier against further corrosion. The formation of this layer requires specific conditions of heat, humidity, cycling, and phosphorus content in the metal that the pillar's compositio and Delhi's climate happen to provide in almost ideal proportions. The conventional explanation is that this remarkable corrosion resistance is the result of the phosphorus content of the ore used, the forging technique applied, and a favorable accident of the local climate. And this explanation is almost certainly correct. What it cannot quite explain is how a 4th century metallurgist produced iron of a purity and phosphorus composition that modern researchers spent decades trying to replicate, and that the best efforts of the replication still have not perfectly matched. The Nazca lines of southern Peru are, in the most basic terms, a set of geoglyphs designs made by removing the reddish-brown iron oxide-coated pebbles of the Nazca Plateau to reveal the lighter ground beneath. They were created by the Nazca culture somewhere between 500 BC and 500 AD, across an area of approximately 450 square kilometers of desert plateau. The lines include perfectly straight lines that extend 4 kilometers across the desert without deviation. They include geometric shapes, triangles, trapezoids, spirals of extraordinary regularity, and they include figurative images, a hummingbird, a spider, a monkey, a condor, a human figure sometimes called the astronaut, drawn at a scale of hundreds of meters with a fluid, single-line quality that suggests each figure was conceived as a whole before it was executed. The conventional explanation for the Nazca lines, and the one that archaeological evidence most strongly supports, is that they were ritual pathways, walked as part of religious and ceremonial practice related to water, fertility, and astronomical observation. The Nazca people were sophisticated astronomers. The desert plateau was their sacred landscape, and the lines were a way of inscribing meaning onto the land at a scale that connected the human community to the cosmos above it. This explanation is coherent and supported by significant evidence. It does not require the lines to be visible from the air to function. The act of walking them, of moving through them, would have been their primary purpose. But there is an aspect of the lines that the ceremonial pathway explanation does not address with complete satisfaction: the precision. Several of the perfectly straight lines on the Nazca Plateau extend for distances of up to 20 kilometers without deviation greater than a few meters. Achieving this level of straightness across broken terrain, using only the technology available to the Nazca culture, requires either a surveying system of considerable sophistication, one that no corresponding tool or artifact has yet been found, or a method of measurement and correction that modern engineers, when asked to consider the problem, tend to find more challenging to reconstruct than the result makes it appear. How they did it, exactly, is still an open question. And open questions, in a landscape as carefully made as the Nazca Plateau, deserve patient attention. At an altitude of approximately 3,800 meters above sea level, on the Bolivian Altiplano near the southern shore of Lake Titicaca, there is a site called Puma Punku, a Tiwanaku word meaning, roughly, Gate of the Puma. It is part of the larger Tiwanaku archaeological complex, and it is one of the most genuinely puzzling engineering sites of the ancient world. Puma Punku is a field of megalithic stone blocks, many of them carved from andesite and red sandstone that once formed a large ceremonial platform and associated structures. The site was substantially demolished, probably by a catastrophic flood or earthquake sometime around 1000 AD, and what remains is largely a scatter of the original components. But those components, examined individually, produce a consistent reaction of disbelief in the engineers and stonemasons who study them. The cuts are too precise, the right angles are too exact. The interlocking geometries, the H-shaped blocks, the perfectly rectangular recesses, the matching indentations that would have connected separate stones into a unified surface, are machined to tolerances that, when measured, approach those of modern precision manufacturing. The surfaces are flat to within fractions of a millimeter across spans of several meters. The corners are sharp in a way that hand tools, working in the material available, should not consistently produce. The Tiwanaku culture had no iron tools. The softer metals available to them, bronze, copper, are not, in the conventional engineering assessment, capable of producing the finishes seen at Puma Punku in the quantities and at the consistency represented by the surviving stones. The conventional explanation invokes stone-on-stone abrasion, the gradual grinding of surfaces against each other, combined with sophisticated templates and a level of skilled labor whose precision, while impressive, is not categorically impossible for a highly organized society with abundant time and incentive. And this explanation is not falsified by any existing evidence. It is plausible. It is what the academic consensus offers. What it lacks is a demonstration, a working recreation of the technique at comparable scale, producing comparable tolerances using only the materials and tools the Tiwanaku are known to have had. That demonstration has not been produced. The precision of Puma Punku remains, in the precise sense of the word, unexplained. In 1999, a geology professor named Alexander Chuvirov at Bashkir State University in Russia was searching through archive records from the 18th century for references to Chinese migration into the region when a colleague drew his attention to a reference to a stone slab, a large, heavy, peculiarly carved stone that a local landowner had apparently used as a doorstep for generations. Chuvirov found the slab. It weighed more than a ton. Its carved surface, when cleaned and examined, appeared to be a relief map, a three-dimensional topographic representation of a portion of the Ural region, rendered in extraordinary detail, with river systems, mountain ranges, and what appeared to be an elaborate system of channels or irrigation features cut across the landscape. The material of the slab was identified as a fused composite of dolomite, calcium porcelain, and a third substance that the initial analysis could not identify with certainty. The dating of the object, based on the geological formations it appeared to depict, and the position of certain star formations encoded in the map, led Chuvirov to propose a date of creation of approximately 120 million years ago, a date so extreme that it was immediately, and reasonably, dismissed by the broader scientific community. Subsequent analysis has placed the slab's creation at various points within human history, with more conservative estimates suggesting it may be 3,000 to 5,000 years old. At that age, it would represent a sophisticated topographic mapping capability in a region and period for which no comparable tradition of cartographic skill is documented. What the slab is, precisely whether it is what Chuvirov believed it to be, whether its apparent cartographic features are intentional or pareidolik, whether the composite material of its construction reflects an advanced technique or a naturally occurring formation has not been resolved by any peer-reviewed analysis that the broader scientific community has accepted as definitive. The stone sits in a museum. The question of what it is remains, quietly, open. 7 objects. 7 moments in which the archaeological record produces something that the surrounding context cannot fully absorb, something whose existence is documented, whose physical properties are measurable, but whose origin and meaning and the full scope of the knowledge that produced it remain, in each case, imperfectly understood. The conventional wisdom about ancient technology tends to follow a relatively clear trajectory, from simple to complex, from crude to refined, from the stone tool to the silicon chip, in a line that, while not perfectly straight, moves consistently in one direction. Progress, accumulation, the irreversible advancement of human capability over time. What these 7 objects share, what the Antikythera Mechanism has in common with the Delhi Iron Pillar, what the Nazca lines share with the precision of Puma Punku, is that they do not fit that line cleanly. They appear at points in the historical record where the surrounding evidence does not, by itself, predict them. They represent capability that arrived, flourished long enough to leave a single extraordinary example or a field of astonishing cuts in stone, and then disappeared, swallowed by the same processes of loss and forgetting that have erased so much else. The honest position is that this can be explained. Knowledge is fragile. Civilizations collapse. Libraries burn. Traditions are interrupted by plague and conquest, and the slow dissolution of institutions that took generations to build. The loss of sophisticated knowledge is not mysterious. It is, in the historical record, almost the rule. But what is worth sitting with what these objects, taken together, quietly insist upon, is that the loss was real. That there existed, at various points in the human past, levels of understanding and capability in specific domains that exceeded what we have assumed those times and places could produce. And that we are working, in almost every case, from the ruins of a record that was never complete to begin with.
The Antikythera Mechanism spent 2,000 years on the seafloor. The sponge divers almost didn't stop at that island. The storm that drove them there was, by any account, a matter of chance. What else is still down there? In the sediment, in the sand, in the archive rooms of museums that have not yet found the time to look carefully at everything they hold? What other corroded lumps of bronze are sitting in catalogued obscurity, waiting for someone to notice the gears? That question does not have an answer yet, but the fact that we have to ask it at all says something about the past that we have not yet finished learning how to hear.